Das ist nochmal so wild. Das kannst du einfach nicht so klicken oder nicht.
Yeah, good morning, everybody, and welcome to the third day of our summer school. We start this morning with a really interesting and important topic, especially in data analysis. Inverse problems. And for this topic, we have a speaker here, Michael Schmelling. He's professor at the Max Planck Institute for Nuclear Physics in Heidelberg. Actually, he got his PhD here in Dortmund. So welcome back. And after a postdoc in Mainz and also fellowship and working at CERN, he got his position there in Heidelberg. And his research is focused on particle or nuclear physics and hadron colliders, and including, of course, the analysis, the data analysis, and its numerical and statistical methods. Therefore, we here have an expert for the topic inverse problems and their solutions.
Okay, so I think I'm sufficiently wired so that you can hear me. There's a nice introduction. Actually, I mean, these inverse problems, something I already did in my PhD. So I'm guilty of working for many decades in this field. And so I can give you some inside views of what I learned in the meantime. So as a logo of this school already tells you, the problem is in principle not solvable. So, but I can tell you what I can do nevertheless. So this is a short map of what I'm going to talk about. After a brief introduction, I will do the first, the obvious thing, unfolding matrix inversion to solve the inverse problem, and then go through some in-depth analysis of what's going on here, discuss some common methods which are currently used by many people to do this kind of unfolding, before I then turn to the most important part of this lecture, namely to talk a little bit about the so-called posterior response matrix, which is very important to judge what the result of some unfolding procedure gives you, before I finally end up at the summary. Okay, so let's get started. So the unfolding problem or inverse problem is very simple in principle. So you have some true distribution f of y, which you want to measure, but your detector is not perfect. So you have inefficiencies, you have systematic shifts, you have finite resolution. And so this is what the detector does. It's described by a response function, which I here will call r of x comma y, where x is observed observable and y is a true variable, which is a distribution, what you see in x for every y that is there in reality. So it's a probability distribution in the end. So in this case, then you can write the observed distribution g of x that you can observe as an integral over the true distribution, where you multiply the true distribution by the response function, r of x comma y. So that's sufficiently simple. And it's a very common problem, as you already see here, because this r of x comma y has different names in different communities. So experimental physicists call it a response function. The astronomer calls it a point spread function. The theorist calls it a Green's function, and the mathematician calls it a kernel. So it's always the same thing. And this tells you this kind of problems is quite common, and it's very important to understand what you can do and what you cannot do. So an unfolding in this case means that you want to get an estimate for the true distribution f of y, given that you know the response of the detector. You have a sample of any events which you draw from the measured distribution g of x. That's the problem you want to solve. So in reality, you have the measurements, particle physics, typically events, let's say 10,000, 100,000, whatsoever. You know in principle what the detector does, or at least you think you know. And from that, you want to estimate what is the true distribution f of y, which is distorted by your measurement process. Okay, regarding this lecture, please, whenever there are questions, just interrupt and ask, because I think it's much better to give immediate feedback rather than postpone anything to the end. Okay, so the first thing we have to talk about is discretization. So, as I already told you, this g of x here is sampled only for a finite number of events. So you have only a finite number of events, which means the available information that you have to work with is really finite. That means if this f of y is really continuous, you cannot never get a really truly model independent unfolding, because the continuous distribution is defined on infinitely many points. So you need infinitely many measurements, and you have only a finite number. So you have to something to do to deal with the fact that you have only finite information. So as a consequence, the problem has to be discretized. So in other words, you describe your f of y with a sufficiently large number of parameters that give you the shape of this function. Okay, if you have a theorist who tells you, okay, the functional form is just a straight line, then you have two parameters, it's very easy. But in case you don't have this information, then you need some more generic model. And in that case, you come to what we call the proper unfolding, let's say, where you expand your true distribution and also the observed distribution into some basis functions, which you may call alpha of k and beta of L. And these basis functions can be anything. So this can be harmonic functions, but then it gives you Fourier components. You can use orthogonal polynomials. You can use histogram bins, which are sort of zeros order splines, also orthogonal ones. And there's many, many other possibilities. But just for simplicity, let's now focus on just one case, namely discretization by histograms, where for simplicity, we also take the constant bin width. That means we describe our measurements not by the continuous function g of x, but by some integrals over this function from xk minus 1 to xk to give you a coefficient ak. So that's the histogram of the measured distribution. And likewise for the true distribution, integral over y, f of y from yi minus 1 to yi gives you the true bin content bi. So the thing is that in this case, you have a very, very simple intuitive interpretation of what these coefficients mean. Histogram tells you immediately how the things look like. It's a very crude and basic identity estimator. Also, you make no assumption about smoothness of curvature of the distribution. You just say, okay, that's the integral of a certain range. That's my bin content. So now let's look at the discretized unfolding problem. So you have then this ak here, it's the integral over dx g of x over the bin width. So then you substitute the definition of your g of x, the relation to f of y, so the integral over f of y with the response function, so this convolution here. Okay, and then you can write this integral as integral over the bins, sum over I over the individual bins of the integral. In the next step, you make an approximation. You say, okay, this f of y here is basically the bin content divided by the bin width. So that's just assuming that you have a step function. And you see here you do an approximation. So in the next step, then you see now you're already there. You have here a sum over I with some coefficients rki times the bi, and the rki you can read off here. That's 1 over delta y integral dx dy over the bin of your response function. So now you have simplified things a lot. So of course you need a sufficiently large number of bins in order to limit the quantization errors which are involved in this game. But now the unfolding problem really becomes a problem of linear algebra, which you know how to solve. In other words, you have your measurements A, the response matrix R times the truth B. Very simple. Okay. So now to work with this, we need a toy model. And this is now really the most often unfolded distribution of the world. So this is a PDF, which is a sum of 3 terms, 5 Wigner terms. So this is something which has peaks and a smooth background. The response function I will use in the following is this one here. So it gives you the distribution of x given a true value of y, which has a Gaussian term, 1 over 2 sigma squared x minus nonlinear function of y. So in other words, there is some bias times and some resolution. And there's also some efficiency function, 1 minus some term which is 0 in the middle and drops towards the end. So in other words, in the current game, we will use a Gaussian resolution when we do some unfolding. Sorry. So sigma of 0.005. This bias here, this beta, will be taken 0.1, and this alpha parameter here will be taken 0.5, which means that towards the edges of the phase space from 0 to 1, you have an efficiency loss of 50%. Okay, so these are formulas. It's nicer to see what this really means in practice. And I hope this will now work. Yeah. Okay, so I need to get rid of the Zoom window somewhere. Good. Okay, so this is now the toy model I'm talking about. The true distribution is here. The observable distribution that you can see is here, given the response function, which is illustrated at this point here. So it's between 0 and 1. So I give you the expandable of the response at some discrete values, 0.1, 0.2, and so on. And you see there's a delta function where I put it, and then there's a small Gaussian around it, which tells you what the resolution or what the response is here. And this is really a very good response. So the average measured value is at the true value. There's no bias, the resolution is very small. So you see the observable distribution is very similar to the true one. Now you can see what happens if you have, for example, a bias term, when the measured value is different from the true one. So it's a small bias here for small values of x and a large bias for larger one. And you see if you increase the bias, you shift the upper peak closer to the lower one. So if you have efficiency losses, that means you see it here. So the delta function that you put in as in your true values are still remain the same, but what's observed is less, here is less, and then it gets slightly higher up, and the middle is again 100%, and it drops towards the end. So you see that's the effect of efficiency losses, and you see how it distorts the distribution. So in the middle, nothing happens, but at the edges, it's getting suppressed. And then if you have also a finite resolution, you see what happens. So the peaks get broader, you get some smearing out of the phase space region that you put in, so it's something below 0 and above 1. And if you have all together, you get these kind of effects. So now the task is, you have some events drawn from this distribution. you know what the detector is doing. So now basically you know what the response function here, and you want to get back to the true distribution. Okay, so in this toy model, we always take the response matrix to be exact. So in other words, we have no quantization errors, we ignore those. We restrict the true and observed distribution to the same range, 0 to 1. That's not really necessary because the observed distribution is wider. But in order to make things simple, we can only look at the part which is also overlapping with the true distribution. We have NA bins for the observed distributions and B bins for the true distributions. And the true distribution is B, the observable distribution is the expectation value of A, and the actual values are A, the expectation value plus some random variable which fluctuates or up or down. So the fluctuation of the expectation value of 0. So in other words, on average, you get the correct value, but the specific measurement may deviate. And the size of fluctuation depends on how many events you have. So in other words, if you have many events, then relative fluctuations are small. If you have few events, they are large. Okay, now let's solve the discretized problem. So we do unfolding by matrix inversion. That's the obvious thing to do. I mean, we have our relation. Measurement is response matrix times truth. So the truth is inverse of the response matrix times measurement. And if you do that, you can also give the covariance matrix of your measure. So the unfolding result of error propagation, it's R to the -1 covariance matrix of R times R to the -1 transpose. This method is formally perfectly correct. It gives you an unbiased estimate for the truth. It gives you also a proper covariance matrix, in other words, proper errors. And the third thing is completely useless. And this is what I want to show you here. Okay, so we have here the observed distribution. So what you expect is a red histogram here. What you actually see, the points with the error bars are the actual data, they fluctuate around the red curve. So then you apply the inverse of the response matrix, then you get this one here. So the unfolded result is the points with the error bars, which are, well, compared to the truth, yes, they are consistent probably, but actually what you see here is pretty much useless. If you look at the correlation coefficients of these errors here, you see it's really a checkerboard pattern. In other words, adjacent is 100% anti-correlated. Of course, if you take this unfolding result here, the blue points with the error bars, multiply with the response matrix, you get the light blue histogram here, which is exactly the data. So that works. So this was now here for an observed distribution which contains 10,000 events. You can now see what happens if we take, let's say, 100,000 events. Doesn't look much better, right? 1 million? No. 10 million? Yeah. 100 million? Okay. 1 billion? Aha, we are getting there. Or 10 billion? Okay, so now we got it. So in other words, this tells you immediately that unfolding is probably something which is very hard, because you need, in this simple case here, already 10 billion events to get a reasonable estimate for the true distribution based on matrix inversion. So maybe we were too ambitious. So what happens, for example, if we go back to 10,000 events and say, instead of 20 bins, let's take 10 bins. Yeah, that works, more or less. I mean, it's not really something you're thrilled about, because, I mean, this is very coarse, the error bars are large, so what happens if you go to 11 bins? Yeah, 12 bins. Okay, it's getting worse and worse, 13 bins. Now still some resemblance to the truth. 14 bins. Now we are losing it. And so you see, apparently, with 10,000 events, we can just unfold up to 10, 12 bins or so. And if we go to 20 bins, we already need 10 billion events to get a reasonable result. Okay, so let's try to understand what's going on in this game here. So, and let's do a little bit of what I call here information theoretical analysis. Again, for our simple toy system, or not even more simpler toy system, by the way. So we consider a uniform density f of y on the range 0 to pi. So the most simple thing you can imagine. And then you consider 4 effects of a detector, a perfect detector that your response function is just a delta function. You measure what's there. Second case, you have some bias in your detector. In other words, what you measure is shifted from the true value. It's the function of the true value. We have put this function here, which is just built such that it is for y equals 0, it's y, for y equals pi, it's again pi. That's how it's constructed. Otherwise, it's some nonlinear function in between. So you can also imagine efficiency losses, that what you measure is at the true value, but with a finite efficiency. So you do not see everything, but some events are lost. Where you use again a parabolic efficiency function here. Or you look at finite resolution. So just a Gaussian resolution of your x around the true value y. And now let's see what this function here really look for the simple case that f of y is just a uniform density. Okay, here you see it. So this is your response function. It goes from 0, 0 to pi, pi, some nonlinear part. And if you put in some uniform f, the red curve here, what you observe is this distorted thing here. This is for 20,000 events. If you have efficiency losses only, then you see this is a perfect straight line on the diagonal from 0, 0 to 1, 1. But you have more entries in the middle than at the edge. So you see what happens of your uniform distribution. It just becomes this parabola. And if you have some resolution effects, okay, then you have on average here the diagonal from 0, 0 to pi, pi. But there's some smearing around. So for the true value y, there's then smeared around some x values where the expectation value is a true value, but individual measurements can deviate from that. In this case, the picture looks like follows. So you have again, you are in the middle, nothing happens, but you see at the edges, there's a smearing effects. Okay, so next, we expand the true distribution into some orthogonal functions. And here I use this expansion here. So I expand f of y just into a cosine function, okay, with 0 to infinity with some coefficients ak, cosine ky. So these are plotted here. So this is k equals 0, it's just a constant. K equals 1 is a function with 1 knot, k equals 2 has 2 knots, 3 knots, and so on. So in other words, these basis functions really probe the properties of this f of y at different resolutions. And as you see, the coefficients ak are associated with functions which have k equidistant zeros. In other words, this ak probes information related to histogram with k plus 1 about equal size bins. So that's the rough picture that you should have in mind here. Then we can now quantify the effect of the detector response via the so-called Fisher information. So this is statistical information which tells you the information about a parameter A that you can get from an event drawn from a density rho of rho, which is a function which depends on this parameter A. And that's how the definition is of this relation. I don't want to explain this in detail how this comes about or where this comes from. It's just the expectation value of some logarithmic derivative squared. And the importance of this quantity comes from the fact that this is the inverse of the minimum possible invariance that you can have for an unbiased parameter estimate for A based on a measurement drawn from rho. This is so-called Cramer-Rao inequality. In other words, it tells you how much information about this parameter A you get from a measurement which is drawn from this distribution rho. So if the information is large, then you get a very precise measurement. If the information is small, then the measurement is very unprecise, has a large variance. And now we can describe the effect of the response function by attenuation factors, which I call omega k. So in other words, you compare the information about this coefficient ak that you get from the observed distribution to the information about ak that you have from the true distribution. So this tells you how much information you lose by having this detector response, which relates f to g. And since this model is sufficiently simple, you can actually calculate these attenuation factors just for this f of y constant density. And that's the result. So for the pure bias term, all the omega k's are 1. There's no information loss, which makes sense because the bias just tells you, okay, I have the true value y, I measure x, but I know the distance between two, so I can just shift back, recalibrate, and that's it. So the efficiency losses here, in this simple case, are also small loss of information. So omega 0 is actually 1, and omega k is 1 minus a small correction term, which goes to 0 for large k. So in other words, efficiency is also not a problem. The problem is resolution, because then you have a massive loss of information. And here you can really, well, this is a numerical calculation, because even in this case, the simplest model I could conceive of was not possible to give you a closed form analytical solution, except for some asymptotic terms. So you see here how the information is attenuated as a function of k. So low order terms are still pretty high, but then they drop off, and this is a log scale. So exponentially the square of this k. So e to the minus k squared sigma squared. So you lose rapidly. So already at 10, you are at a 1,000th of the information that you had for the undistorted measurement. So interestingly, this rapid exponential drop is attenuated, then here it goes off to power law. This is in fact due to the boundaries, if you look at the mass of your problem, because, let me go back just, the fact that you have only between 0 and pi is a lot of information, and that information really pays off in the end in this attenuation factor. So this power law tail here, that is due to the fact that I know that my distribution is bounded. If it were unbounded, then this red curve would continue forever. So I think we know at this point why unfolding is so tough, because the resolution just kills information rapidly. And it also tells you, okay, well, it's very hard to go to really high orders. So you will only get access to the low order terms of your expansion of the true distribution, which you can really extract from the data. The higher order terms are just lost. So, are there questions at this point? Oh, everybody is sufficiently frustrated with the fact that it's so hard. Good. Okay, so then let's talk about some stable methods that people apply to correct for the detector effects. So the first thing I would like to address is bin-by-bin correction factors. That's a time-honored technique which is being used since I think the dawn of at least particle physics, and it's still in use today. So here you use the same binning for observed and true distribution, and you define bin-dependent correction factors. So every bin is corrected. So you have a measurement, AK, you multiply with the correction factor CK and get the estimate for the true value BK. Very simple. And the determination of these correction factors is you start with an assumption about what the BKs are, then you determine what AK you would get by multiplication with the response matrix. So in other words, your AK is just the response matrix multiplied with the assumed beat. And then you know what the correction is. Oops. So the correction factor is the BK that you put in over the AK that you observe in this case. So, of course, there are some caveats here. So this correction factor depends on what you assume for the true distribution. So if you take different BKs, you get different correction factors. So in other words, it's good if you roughly know what you expect. And that's what people do if they run simulation. So if you have a Monte Carlo model for your process, then, okay, you put in something for the truth, which is probably reasonable. And then you get also reasonable correction factors. You can, of course, be very brave and say, okay, let's take the objective and say, we don't know anything, so we just take a uniform distribution for the BK that we put in and get the correction factors then also out of this. This will be different corrections. Or you can say, if I don't know the true distribution, I take the measured distribution instead, because I hope that my detector is not so bad. So in other words, this measured distribution will be similar to the truth. Okay, evidently, the correct result, that, in other words, really correct correction factors are guaranteed only if you take where you estimate the true distribution. But in that case, you haven't learned anything. So this is not really the interesting case here. But even if you only know approximately what you expect, then probably some correction will be achievable. But of course, it's always good to check in a model how well this really works. So before doing this, let's do something more and say, okay, if we have correction factors which depend on what I put in for the BK in the first place, well, maybe I can get independent of this assumption by iterating. In other words, I say, okay, do an initial iteration, say, okay, I assume first my correction factors, my true distribution is the same as the observed distribution, then get correction factors. So then I get some corrected BK, which I then can again use as an input to get new correction factors and iterate until this really converges. So this I also would like to try now in an example here. So, okay. So what we see here is the following. Same game as before. We have observed distribution, just 20 bins. The actual data in blue scatter around the expectation values, which is given by the histograms. So then I do on this side here, the blue points here are uniform distribution, which are assumed, okay, that is my truth estimate. And if I convolute this blue points here with the response matrix, then I get the light blue curve on the right-hand side. So on the ratio between this loop curve on the right-hand side over the light blue on the left-hand side, they give me the correction factors which I should apply to this blue points here to get an estimate for the true distribution. So we do that once. That's what we get. Okay. So we see after this first correction step, I'm certainly closer to the truth than before. Before it was flat, now it's at least following this two-peak structure. And if I convolve this again here with a response matrix to get the light blue curve here, you see I do not really describe the data yet. So this correction was probably not sufficient. So I do it once again. So again, take the ratio of this side, blue points, to this side, light blue. As a correction factor, apply it again. Okay. Yep, it helps, but it's still not perfect. So I can iterate, and I can also just let it run. Hopefully they will converge eventually. And what it does, yes, it converges, but certainly not to something I like. So we can go back and do the same game here again, assuming that for the first correction step, I know the truth already, and then I do a correction, and then I see, okay, this is nice. But also, if I iterate in this case, things become unstable. Or if I take as a first step the observed distribution, do a correction step, you see this was not a good idea in this case, because the corrected distribution actually looks worse than the uncorrected one. But also here, if I let it run, I get the same result. Okay, maybe I was unlucky here because I had some bad starting values, some bad fluctuation in the beginning. But also if I have another data set, I get a very similar picture. Not exactly the same, but something again which doesn't make sense. Also, I mean, the error bars which I draw here are just the uncertainty of the measurement times the multiplied with the correction factor. These error bars don't make any sense. So these correction factors, which are, as I said, a time-honored technique to correct data, are not without problems. So you see these correction factors work well if the true distribution is known. Then you don't need any iteration, but you also don't learn anything from the measurement. There's also some conceptual problems in this. I mean, first of all, empty bins are always corrected to 0 because you can have a 0 and multiply with anything, you will always get 0. And data outside the physics phase space are ignored because you cannot, multiplying something from outside the phase space, you will not bring it inside the phase space. So the iteration, however, removes the dependence on the unknown distribution, but this naive error propagation is clearly wrong. So if you want to do proper error analysis, then you can do, for example, pseudo experiments. In other words, you generate capital N pseudo samples, let's call them AM, just by fluctuate the data that you have within the uncertainties. So then you get, that's a kind of bootstrap approach. So for each of these pseudo samples, you determine an unfolded distribution, so corrected one, with m times iterated correction factors. And then you average the unfolded distribution to get the nominal result. So you take the expectation value of these m values here for your unfolding result, and the corresponding expectation values for the covariance matrix to give you the proper errors. So I also implemented that one. To tell you that this method in principle works. So now what you have here, move this away. So you have this observed distribution again. Then you have an unfolding result with 10 iterations of correction factors. Then you get, for example, the blue histogram here. And you do this repeatedly. So this was now one result. You take a second result, you get fluctuating the measurement, third result. And then you have now enough statistics to do some averaging and also get some estimate for the correlation coefficients. And you see what you have. So fluctuating these blue points here within their errors, and then doing the unfolding by 10 times iterated correction factors, you see how this scatters here. But the average of this whole game is this one here with the error bars, which is, as you see, if you do the proper error propagation, this is consistent with the truth. And you also see how the correlation coefficients are. You have large correlations here in the, well, of course, there's one on the diagonal, but then it's anti-correlated in neighboring bins, and then there's some scatter around. So now you can do different things. You can also do, say, okay, I take fewer iteration steps, let's say only 4, and see what happens in that case. So you see, fewer iteration steps give you some more precise result. And if you say, okay, I iterate more often, let's say 100 times, so in other words, if you want to do a better job, iterating more often, getting completely independent of your starting values, then the result becomes worse. So that's, of course, pretty much frustrating. So in other words, you get surprisingly large errors and strong correlation in the unfolded result. And actually things get worse the more work you put into it. So that's the reason when experienced people tell you, do the correction once, and that's it. With the caveats which I mentioned before. Okay, so there's another quite popular method to do unfolding, which is called this Lucy-Richardson-D'Agostini unfolding. The literature is mainly Lucy-Richardson. D'Agostini is more recent. So this guy here comes from astronomy. This guy is from optics, and this is particle physics. And I think they're more or less, I think the first two published together, but this guy here maybe invented it independently. So in other words, here what is done here is you interpret the response matrix as conditional probabilities. So what you do, you decompose your RIK into efficiencies epsilon k in a pure smearing matrix Sij. So this RIK then you can write as RIK of epsilon k times epsilon k. And the first term is then the smearing matrix, the other one is efficiency. Efficiency is just about the sum of the other final state. In other words, what's the probability to see anything if you have a true entry in bin k? So then you interpret this Sik as conditional probabilities. You say, okay, Sik is the probability to observe something in bin I if the true entry is in bin k. And then you can use Bayes' theorem to invert these probabilities. That's also why this kind of unfolding is also called Bayesian unfolding. So you can say, okay, what's the probability to be in the true bin k if the observation is in bin I? Okay, by Bayes' theorem, this is again P observed in I true, is a true in K, the probability to be in true. You normalize to the probability to observe anything in I. And all these terms we know here in this game. This is a smearing matrix. This is a true distribution PK that you have. And this is here then again, the observation is just a convolution of the truth with the smearing matrix. So, and here you can, for example, assume uniform prior probabilities for the P true of K, and then you get some result. I mean, and you can, of course, again, you can iterate this in order to get rid of this initial assumption. In other words, you repeatedly apply this H to your data. And finally, when you're done, say, okay, this is converged, you apply the efficiency corrections, and then you can also, again, as before, do the error analysis for this game, as before, by fluctuating the measurements and doing everything over and over again and to see how things fluctuate. So also this is here something I would like to show you. And that's also, I think, important because this method is really heavily used these days. So again, 20 bins we have here. We have a measured distribution which fluctuates around the expectation. We have here unfolding by 10 iteration steps in this Bayesian unfolding. And we can fluctuate the data and then see how the results turn out to be. Okay, so you see, this is why people like this method. It doesn't explode so fast. You iterate, you get something which is reasonable. And you look at the correlation coefficients here and see, okay, there's a strong correlation in the middle. So, and then it goes into anti-correlated in neighboring bins. And then it's slightly negative everywhere else. So this was now after 10 iteration steps, and you see the result looks reasonable, except that it's maybe not really consistent with the truth. Let's go back one step and say, okay. What happens now if you take more iterations in this method? More iterations helps in the sense that now your unfolding result is consistent with the truth, but also your error bars are larger. In the correlation matrix, it's also narrower here, so it tends to come towards this checkerboard pattern that we saw in the beginning for the matrix unfolding. So in other words, if you summarize what we learned so far, this Bayesian unfolding certainly is a mathematically sound approach. It uses explicitly that you're using probabilities which are positive. So you can move measurements from unphysical regions into the allowed phase space. That's also good. You don't need any to matrix inversion. This works also for non-square matrices. Also, if you look at it closely, implicitly, you do some matrix inversion just by iteration in the end. So iteration again removes the dependence of the initial estimates for the prior. That's also good. However, if you have too few iterations, the results are correlated with what you put in. If you have too many iterations, then the result again becomes unstable. But people never go so far. They just stop when they think it looks nice. And yeah, it's not clear to me actually. I mean, whether this converges to something reasonable, or whether it maybe does not converge at all if you have increased the number of iterations. But what you also see is that the iterations correlate with the structure of the covariance matrix. In other words, if you have more iterations, your covariance matrix becomes more narrow and more stronger anti-correlated. And here the unfolding algorithm is really defined by the number of iteration steps. So if you take 5 steps, you get different results from 10 steps. If you take 100 steps, yeah. What people typically do is they run the algorithm, say, okay, when my next iteration step gives me a change of only 1%, then I stop because then I call it converged. But in fact, it is not converged. They would get still small shifts if they would continue. So I think at this point, we have seen some unfolding methods which more or less work within limits. You also see the problems. And I think we need to really do some systematic analysis now to see what is the effect of the different regularizations. In this case, we're always, how many iterations do I apply? So, and this brings me to really, I think, the core of this lecture here. So the estimate B for the true distribution is just a function of the measurements A. If you put some algorithm, you put in some measurements, you crank it through, and then you get the result. So in other words, B is a function of A. And if you want now to calculate the uncertainty of your output, error propagation, the covariance matrix of your B, C is then M times C M transpose, where this M is just a Jacobian. How does your BK change for any change in AI. So this Jacobian you can have maybe as a byproduct of the algorithm. It can be always estimated if you just do numerical differentiation. Otherwise, you vary your inputs and do the differentials. And of course, you get a perfect unfolding if this M here is just the inverse of the covariance, the response matrix. So, however, now let's look at this. If this M here is given, then we can define two characteristic matrices. The first one I will call here the regularization matrix. So, starting point here is that if you have some estimate B, you can multiply it with a response matrix to get again something which should be the A, but it's an estimate for this A. So this is R times F of A. So these A hat here are in fact some smooth values of the actual data. We saw this in some examples before. And they should be consistent with the actual data. Otherwise, your estimate for B doesn't make any sense. So now the key is you want to determine the sensitivity of this A hat to variation in the measurement. In other words, you want to measure the elements Qij. How much does my smooth value AI hat vary if I vary the input Aj? Okay, you can write this down, just a chain rule, dA hat to dbk times dbk to dAj. And these terms you can identify here. So the first one here, dA hat to versus dbk, that's your response matrix. The second matrix, dbk to dAj, that's the Jacobian M. So in other words, you have the matrix Q times R times M. So that's the matrix of dimensions of your measurements, Na times Na. So and this Q measures the damping of the fluctuations by the unfolding algorithms. So if, for example, you have dAi hat, over dAi equals 1, then they follow 1 to 1. There's no regularization, there's no damping. In the other extreme case, if this differential here is 0, it basically means your measurement is ignored. So, and that tells you, okay, if you just look at the diagonal of this Q matrix and sum the elements, in other words, take the trace, that counts how many of the measurements effectively contribute to your unfolding result. If this trace here is Na, then all your measurements contribute. If it's smaller, then only some of the measurements really have an impact on your result. So this is some kind of effective number, and effective, which is a trace of this matrix Q. So that's already quite interesting, I think, to see how many of your measurements actually are able to contribute to your result. I mean, that don't already fully contribute. It's just a consequence of the fact that your statistical fluctuations. So these are taken sort of damped by this iteration procedure, which you stop at some point, and then you get a result which does not really take all the values that you have in your data at face value. So the second matrix I would like to talk about is here, the posterior response matrix. If you consider the sensitivity of how the unfolding result B changes if you modify the true distribution. So in other words, I'm interested in what's the relation between the unfolding result dbk with respect to dBl of the true distribution, which I don't know, but no, this doesn't stop me from doing this derivative. So again, as a chain rule, I can write this as dbk versus dAi times dAi with respect to dBl true. So the first thing here is again just a Jacobian which we had before, this mki. And the second one here is again, how does my measurement change if I modify the truths? This is again the response matrix. So this P is just M times R, so the other product of the two matrices. This is the matrix of dimension NB times NB. So, and you see, this here is really something very important because this describes the virtual detector response between the truths that I want to unfold and the actual unfolding result B. If here the diagonal element is 1, then I have perfect unfolding. If it's 0, then my unfolded result for this bin does not depend on the truth. So in other words, the trace of this P here effectively counts the number of bins which are perfectly unfolded. And the nice thing is here, the trace of the posterior response P and the regularization matrix Q are really identical, because I mean, this is the traces invariant under cyclic permutation of the arguments. So this trace here of this matrix P or the matrix Q is really something which is a core quantity to judge the quality of an unfolding result. And actually this number is then effective is the minimum of NA and NB, so it's the rank in the system. And this one column of P, of this posterior response, describes the response of a delta function in bin K for the unfolding result. So let's look at this a little bit more closely. So we interpret the n times n and b times nb posterior matrix P and see what it means. I can extract from it an efficiency. It's a visible fraction of a signal in bin K. So it's just the elements of the sum of the total column. What it's also telling me is some kind about smearing. In other words, what's the fraction of measurements I, which are not in the bin K where I put my delta function? Okay, that fraction is just the sum over all the column except for the diagonal column I equals K, normalized to the total. And if you see this, I mean, this is just 1 minus the diagonal element pkk over epsilon k. And if you average this smearing here over all the bins, and you see, you come again to the trace of the posterior response divided by the total number of bins, provided that the epsilon k is unity in all the bins. So you see again, this trace of the posterior response is a crucial quantity which tells you what the unfolding result gives you. And if you don't like the smearing quantity but prefer some Gaussian standard deviation, okay, there's a relation. So the smearing quantity here is the error function of the bin width of the divided by √8 times sigma, which you can also invert. If you have the smearing, you can turn that into some Gaussian resolution. And you can also check whether there's some bias in the posterior response. For example, the distance in center of gravity of your measurements compared to what you put in. So the expectation value of your measurement I minus K where you put in your signal. This is then this quantity, so center of gravity minus K. Okay, so let's look again at the Bayesian unfolding for these quantities. Okay, this is the same game as before. So here the blue histogram is expected distribution. The points with the error bars are some actual data sample, it fluctuates around it. Here on the right-hand side, the unfolded distribution, initial steps here, so there's just a uniform distribution compared to the true distribution which I want to get out. And the magenta curve here is just the blue points here multiplied with the response matrix to see how that compares to the data. And you see, okay, the data are inconsistent with the truth being uniform. This is the initial response matrix here from our model. So you see more entries here in the middle. So there's higher efficiency there, less here. You see the bias because the true value here gets mapped to some observed value which is smaller than this, and so on. So now you can, and this is now the response matrix here in these quantities. So you have here there's unity. So here you have in magenta the efficiency, which goes from 50% to 100% to 50%. You have the bias term, which is here this red histogram, which goes a little bit off scale. And then you have the smearing quantity, which is in this case here, so by the blue histogram. Now we do one unfolding step. Bayesian unfolding, single step. This gives you this result here, which is closer to the truth, but not yet perfect. And you see it's also not consistent with the data. The chi-square here is 127. But what you also see here is the posterior response matrix, as defined just before, is basically diagonal, is pretty wide. And the quantities here, so you see the bias here is getting closer to 0. So in other words, this one here is basically a diagonal matrix. The resolution here is actually, the smearing is bigger than it was before after one step. And the efficiency is close to unity, so the efficiency losses are corrected. If I iterate this, you see what happens. I get closer and closer to the true distribution. The posterior response matrix becomes focused on the diagonal. So the efficiency is basically 1 here. So the smearing becomes less and less the more often I iterate. And the bias here is around 0. So the bias is gone. And I can just let it run and see how the efficiency is corrected. So this efficiency is 1 everywhere. There's no bias anymore. And the longer I iterate, the better the resolution becomes. But also, the error bars become larger. So now I have 1,000 steps. And at some point, it becomes again unstable. So let's do this again. So this is again some initial state here. So start with a uniform distribution. And we can let it run. So the unfolding works. And depending on how often you iterate, you get better and better resolution. So less smearing. The smearing goes down and down and down. I should also say, I mean, the dashed line here that you see here, that is just from the trace of this posterior response matrix, the estimate for the smearing, so the average smearing, which compares very nicely to the ones estimates from the individual bins. And you see the longer you iterate, the better the resolution becomes, but also the more unstable your result becomes. Want to see it again? Good. Okay. So to wrap up here, what we've seen in this example here, these unfolding methods, they correct really for bias and efficiency losses. And we saw before in this information theoretical analysis, those are the easiest things. Bias doesn't cost any information, so that's easily corrected. Efficiency losses are cheap, so they're also corrected. But the resolution effects by these methods are at best partially corrected. And if you have some stable method with which your result which you are likely to publish, then you use only the well-measured information. And if that is not enough to really construct your full distribution, then you have to substitute your missing information by some assumption about the smoothness or curvature of the result. You know some a priori knowledge that everything should be positive. You could put in some information theoretical ideas like maximum entropy, and there are many, many other ideas floating in the market. So, but you should always beware. Really model-independent unfolding will not be possible. Forget about it. Unless you have a model, or well, unless you know the 2 parameters that you want to extract, you can do that. So in other words, you always need to find a balance between bias and noise. And how to do this, there's a really huge literature on the subject, and I'm also guilty of contributing to it without really giving a solution, and because there's no really generally satisfactory recipe exists. Okay, so let's talk a little bit more about a systematic approach, how to handle the available information in this game. So this brings me to what I call the Fisher basis, and I derive it for the linear unfolding problem where your measurements are Poisson distributed. So you have expectation values for 2 distributions, BI. You have some expectation values of the measured distribution, which I here call nu I. So this is nu I, that's an R times B, or in component right this way. Response matrix is before R. And the actual measurements AK are then Poisson distributed random variables around these expectation values nu K. So likelihood function for the entire setup is given by this here. So it's just many Poisson distributions. And you have to plug in these. So the expressions are really a bit lengthy, but not completely unwieldy. And now the starting point for the next consideration is again this Fisher information, in this case a Fisher information matrix, because there are many parameters. So in other words, we take the product of logarithmic derivatives of just likelihood function with respect to bi and bj and take the expectation values of the measurement. And after some calculation, you find that in this case, this is R transpose C to the minus 1 R, the C to the minus 1 is the inverse of the covariance matrix of your measurement. So this is a very nasty integral here, but in the end, you get a simple result. And this, as I said before, this I to the inverse of this matrix, inverse of the information matrix, is the smallest possible covariance matrix for an unbiased estimate of B derived from measurement A. So you know that in this case here, the covariance matrix is assumed to be known, where in practical applications, you will have to estimate it from the data. But that's considered as a detail here, because that's again higher order corrections. So this matrix here is symmetric and positive definite, but it's not really very intuitive. So, but we can exploit this property that is symmetric and non-negative by putting it to a diagonal matrix. In other words, if you diagonalize it, this I gets the matrix of eigenvalues E in the rotation matrix V, where these columns of this V are orthogonal eigenvectors of I. So that's basically in the algebra. But the nice thing is you can now expand the solution B into those eigenvectors. So you say, okay, the unfolding result is V times some coefficient vector alpha. And for these coefficients, if you use the eigenvectors of the information matrix, then the information matrix for this alpha is diagonal, just given by the eigenvalues of E. Okay, and that is something you can interpret. So this is for the toy system that is given you before. This is a full matrix, a Fisher information matrix, which is, well, you see there's more information at the edges because everything is limited. And less information in the middle, and it's also somehow spread out. But again, it's very telling you the spectrum of eigenvalues. So that's very important again. So you see this here is a logarithmic scale, 10 to the minus 5, 10 to the minus 8, 11, 14. So it drops like a rock, and you see how the eigenvalues here drop. So the low order eigenvalues are still reasonably large, but the higher order ones are completely inaccessible. So there's very little information in your data about these high order eigenvalues. So if you expand your solution and the eigenvectors of the information matrix, the low order vectors you can handle, the high order vectors you can't. So here are the eigenfunctions of the matrix. So you see the low order ones are still some sort of interesting, but the high order ones just become very similar to simple harmonic functions. And if in this Fisher basis V, you can now do some unfolding, which gives you complete control of what you're doing. That's why I like it. So as I said before, I expand my B into eigenvectors Vk of V. So by the way, if you look in the literature, also a method which is often used by people is the so-called Svd Unfolding method. They use the same basis, even though that I don't tell you. Okay, so then your B is alpha k times Vk. So the alpha k you can get from least squares fit when the data constrain or over constrain your measure, your truth. So you have to minimize the chi-square, A times minus R times the unfolding result, transpose C to the minus 1, and then again the vector. So you have a nice sandwich. And the result from this minimization, you get the alpha k, which are uncorrelated, with variances ekk to the minus 1. So you saw already these eigenvalues, they drop rapidly, so exponentially. So the high order k, the inverse are huge numbers. So they have huge variances. In other words, the high order things, alpha k, cannot be determined. So now you can apply some regularization, just apply a diagonal damping matrix, for example, to suppress the alpha k with large variances, which can be simply say, okay, I look at this matrix and say, okay, I keep only terms up to a certain order, but the other ones to 0. Anyway, so if you have such a damping matrix, then the posterior response becomes this one, V times D times V transpose. So then you can again control things. Okay, so that's one way how to proceed. What people do more conventionally, to not explicitly put the damping matrix by hand, but they use some involved algorithm which hides the details, but also makes things untransparent. That's so-called Tikhonov regularization. So you find a stable solution of your unfolding problem, the minimizing of the chi-square, but different cost function, which you define by chi-square plus w times some s of b. So this s of b is a penalty function, which suppresses unphysical solutions, like for example. So you can ask that the total curvature is small, so you want as straight as possible. You want to have the entropy as large as possible, for example, so you can make an entropy term. You can put here any kind of distance measure from some a priori information. So this is a standard regularization approach. And what you see here, there's one parameter, W, the so-called regularization parameter. So if W is 0, then just minimize a chi-square. You get an unbiased result, but it's also usually unstable. On the other hand, if you take W to infinity, then you ignore your data. You just take the B that minimizes your S of B. So this takes kind of a balance. The problem is, of course, how to adjust this parameter W. And again, there's huge literature on this subject. And again, nothing really works, at least in my experience. And the problem is why you need this parameter is this chi-square and this S are completely different things. And this is a statistical measure. So this is some, and this here is some ad hoc measure. Let's call it entropy or so. In other words, this W is a dimension, is a factor like a chi-square per entropy or something. So some conversion factor between two things which do not really cannot be added. And yeah, so that's where the whole story problem starts. And if you realize that what this W does, then you're wondering, can't you define a penalty function, which maybe also is a statistical measure, because then you can do without the W. And this is now here a basic idea, which you can find, for example, in this article here, where you define the penalty function in units of chi-square. So this is a penalty function. I'm almost done, don't worry. Which is either 0 or +6. So it is 0 if you look for your histogram, the interior histogram, the interior bins, if there's a monotonic rise or monotonic fall. But if the middle point is, then it's 0. So if the middle point is higher or lower than the neighboring point, then you add a penalty of 6. So in other words, monotonic behavior, no penalty. If you have a local extremum, penalty is 6 units. So that means the penalty corresponds to something like between 2 and 3 standard deviation in statistical speak. And you can remove the extremum if it costs less than a delta chi-square of less than 6. In other words, if it's not too expensive, statistically speaking, to get rid of this bump, then you remove it. So in this case, you don't need any regularization parameter W. And the problem is, of course, this is now a discrete non-continuous function, so it's not really obvious how to realize this, because any minimization based on derivatives will certainly fail. And what I can recommend here is what works is you can express your B by independent orthogonal polynomials, basically the eigenvectors of the Fisher matrix. You initialize all expansion coefficients to 0, and then from low to high order, you adjust the coefficient such that you minimize a non-discrete, also a non-continuous penalty function f. That works. So I've given you here again the last example of today. Okay, so this is now again the usual problem, but I have here also other ones to show. So this is something you want to unfold. This is what you measure. So this is the response matrix. And from your Fisher basis, you can calculate the expansion coefficients divided by their uncertainty for all the eigenfunctions here. So, and you see that dividing this by the error gives you how significant are those coefficients. And you see up to 10 or so, you have good coefficients. So you know the coefficients, but the higher order ones are basically noise. And now you can unfold, for example, by the leading terms. So you take the 10 leading terms. You can take the 12 leading terms. You can take the 14 leading terms. 16. And the more you take, the higher your uncertainties here are. So, but the posterior response matrix here, so here it's given the trace here. In this case, if I take 16 terms, it's 16 in this case. You see it becomes more narrow and narrow. That's what we saw seen before. If you unfold and want to correct for resolution, so you improve your resolution, but your uncertainties, the error bars of the result, become larger. So what's plotted here is, by the way, the average posterior resolution, which you just give by taking the average spread here of this matrix here, average of all the bins, and compare that to the black curve, which was the resolution that you put in. So if you have only 10 terms here, you see you get an unfolding result, which looks pretty reasonable, but which has not a resolution here, which is very close to what you put in the first place. So not much gained. You can also compare the unfolding result here. The blue points with the error bars is what you take it if you take the posterior response and multiply with the true distribution, which is again here the magenta one. And you see that's more or less consistent. So more interesting is, of course, this regularization approach, which I just explained with a discrete penalty function. So that suggests here a resolution which is slightly better than the original one. The trace of the matrix here is 12.4, and this is the result here. Okay, we can go to other examples. I think we still have 2 minutes. So because, for example, if you have just 2 peaks, how this you again see how this unfolding improves the resolution. I think what's more interesting, by the way, is maybe the box case. So this is what you observe here by this response matrix. This is a true distribution. If you unfold by the leading terms, 10 leading terms, okay, that's maybe not so good. You take the 16 leading terms, yeah, it's a bit wiggly, but you see the posterior response describes what you see. And if you unfold by regularization, you again see the posterior response is consistent with describes properly how your result is still distorted. You see that the resolution has improved, but you also see there's still some smearing left. Well, you can also look at this example here. If you have an exponential distribution, the same game, you can exponent the cutoff here. If you want to unfold, you cannot really fully do it because there's still some residual smearing, but yeah. And you see this was all done here now without any adjustment of unfolding regularization parameter. Okay, so let's wrap up. Unfolding is an ill-posed problem. So in other words, results are really prone to instabilities, either due to statistical or numerical noise. And here really is a huge literature and heuristics on regularization schemes, how to deal with this. So what you learned here, efficiency losses and biases are corrected. Resolution can be improved, but usually not by much. And if you want to ask for too much, then you lose really severely in apparent statistical precision. So in other words, the error bars become large. So, and you need some information to interpret the unfolding result. You certainly want to give the covariance matrix for the bins of the unfolding distribution. That's standard. Huh? You also want to give some goodness of fit, how well your unfolding result, if you forward it again with the response matrix compared to the data. And I think you definitely want to give the posterior response matrix and at least its trace, because that is the final information, how much your result is still distorted with respect to the truth, whereas the trace gives you the effective number of independent terms in the result, and you can also relate it to the average bin by bin migration by this S1 minus ineffective over the number of bins. And that's finally it. Thanks for your attention.
Yeah. Thank you very much for this really interesting talk. I guess there are some questions.
Thank you. Maybe I skipped a detail, but I've seen, if I got that correctly, that the matrix R of a regularization matrix could be inverted. So the question is, what does guarantee that matrix R could be inverted and the determinant is never zero? Is delta the function that you are exploiting guaranteeing that, or is that something else?
So which function?
Yeah, I'm talking about when you showed actually the perfect detector bias and efficiency loss. So I suppose one of the very first slides.
You mean this here?
Yes, please. Yeah, that one, exactly.
I mean, these examples here certainly are always can be inverted.
Uh-huh.
Yeah.
And yeah, so my question is that, so for example, for perfect detector bias and efficiency losses, is that given by the definition of delta, of that the matrix could be inverted? Because I don't remember the, sincerely speaking, I don't remember the definition of delta, so that's just it.
You mean this delta?
Yeah.
That's a Dirac delta function.
Oh, okay, I see.
So that, in other words, if you look at a discrete thing, that's just unit matrix.
Okay.
So that can always be inverted, clearly, yeah.
Okay, thank you very much.
Ja, du kannst einfach sprechen.
I cannot read it actually.
So that's a question in the remote audience. Mirko, maybe you can talk.
How is the Fisher matrix different from Doble's method, both used for sound distribution and eigenvalue decomposition? Good question. I don't know. I mean, I know that this Fisher answer is the same as the SVD method. I think global is slightly different, but I don't know exactly where the differences are. I mean, also I think global had different unfolding methods published over the years. And
okay, yeah. Can you hear me, by the way? Does it work?
Try again.
Can you hear me?
Yes, we hear.
Okay, so one difference that might be there is maybe the regularization, the damping versus the Tikhonov regularization, but I'm not quite sure because I didn't know about the Fisher method yet.
Yeah. I mean, in the end, these methods always differ in how they do the regularization. I mean, which basis you use doesn't really matter in the end, because you can always transform bases without loss of information. It's more, the basis is more interesting to see where the regularization really hits. At least in my opinion also.
Yeah, okay, thanks. Oh, can I ask another question?
Sorry, yes, you can.
What is like your impression? Are these iterative methods like the one that we have just seen by D'Agostini and the others? Are these iterative methods more, do they work better, or do methods work better that go numerically, like that minimize a loss function?
Well, again, in the end, all are equivalent, but the iterative method has a nice feature that you, it's a different way to do the regularization. In the iterative method, regularization happens by the number of iterations. So you say, okay, my regularization happens by 10 iterations, for example. Huh?
Mm-hmm.
And so you don't have any parameter in the sense like this W in the Tikhonov-Ansatz.
Yeah.
It's more implicit. But of course, you can, in the end, always map one to the other. At least I think you can. So in other words, the iterative methods, this D'Agostini method, is certainly equivalent to some regularization function plus some way to determine the regularization parameter. Whether that's an easy mapping, I don't know.
Okay.
I mean,
thanks.
Yeah. I think for practical application, iterative methods are better because then nobody asks you about the parameter that you choose.
Yeah.
And it's also stable because you look at the result and stop at some point. What I think people should really do in the end when they publish a result is give also the posterior response, because then you know how to interpret the result. And that is so far never given.
Thanks.
Okay, perfect. If there's no other question, I think we're right in time, and thank you again.
There's coffee. Okay, so we have a break now.
Yeah.
Oh, good. Das behalte ich. Der sagt hier Low Battery.
Ja, der sagt die ganze Zeit Low Battery und sagt dann aber 2 Werke.
Warum habe ich jetzt hier 2 Mikrofone gebraucht?
Das eine ist für den Raum, da ist die Anlage so drin. Und das da ist für Zoom, für die Konferenz, weil wir